welcome to this problem walkthrough. Today, we'll be exploring problem number 223, titled Rectangle Area. This problem challenges us to calculate the area of two rectangles on a 2D plane, factoring in any overlapping regions. Throughout the session, we'll discuss different approaches, their complexities, and key insights to help you master this concept. Let's dive in. In this problem, we need to write a function that calculates the total area covered by two rectilinear rectangles on a 2D plane. Each rectangle is defined by the coordinates of its bottom left corner and its top right corner. For instance, one rectangle is represented by the coordinates x1, I1 for the bottom left corner and x2, I2 for the top right corner, while another rectangle is defined similarly with coordinates bx1 by 1 and bx2 by 2. The goal is to figure out the total area covered by these two rectangles, taking into account any region where the two rectangles might overlap. The function signature is provided as compute area, x1, I1, x2, I2, bx1, by 1, bx2, by 2, where all inputs are integers representing the coordinates of the rectangles. The function is expected to return an integer that represents the total area covered by the two rectangles. Let's look at some examples to better understand the problem. In the first example, the input coordinates are x1 equals -3, I1 equals 0, x2 equals 3, I2 equals 4 for the first rectangle, and bx1 equals 0, by 1 equals -1, bx2 equals 9, by 2 equals 2 for the second rectangle. The output of the function is 45, which is the total area covered by the two rectangles, including any overlap between them. Breaking down this example further, the first rectangle spans from -3, 0, to 3, 4, and has an area calculated as width asterisk height, which is 6 asterisk 4 equals 24. The second rectangle spans from 0, -1, to 9, 2, and has an area of 9 asterisk 3 equals 27. Now, the overlapping region between these two rectangles spans from 0, 0, to 3, 2, and has an area of 3 asterisk 2 equals 6. To find the total area, we add the areas of the two rectangles and subtract the overlapping area, which gives 24 plus 27, 6 equals 45. In another example, the input is x1 equals -2, I1 equals -2, x2 equals 2, I2 equals 2 for both rectangles. Here, since both rectangles are identical, they completely overlap. Each rectangle spans from -2, -2, to 2, 2, and has an area of 4 asterisk 4 equals 16. The overlapping region, which is the entire rectangle, also has an area of 16. Therefore, the total area covered by the rectangles is 16 plus 16, 16 equals 16. Now, consider a third example where the input is x1 equals 0, I1 equals 0, x2 equals 1, I2 equals 1 for the first rectangle and bx1 equals 2, by 1 equals 2, bx2 equals 3, by 2 equals 3 for the second rectangle. In this case, the first rectangle spans from 0, 0, to 1, 1, and has an area of 1 asterisk 1 equals 1. The second rectangle spans from 2, 2, to 3, 3, and also has an area of 1 asterisk 1 equals 1. Since these rectangles do not overlap at all, the total area covered is simply the sum of the areas of the two rectangles, which is 1 plus 1 equals 2. The problem also includes constraints to ensure that the input values are valid. For instance, the rectangle boundaries are constrained within -10(4) to 10(4), and the bottom left corner of a rectangle must always be strictly less than its top right corner. This ensures that the calculations are well defined and the result will always fit within a 32-bit signed integer range. To solve this problem, one approach we can consider is the brute force method. The intuition here is straightforward: calculate the areas of both rectangles individually, and then subtract the overlapping area if the rectangles intersect. This involves a few critical steps. First, we compute the area of each rectangle using the formula for a rectangle's area, which is the product of its width and height. Next, we check if there's an overlap between the two rectangles. If there is, we calculate the coordinates of the overlapping region and determine its area. Finally, we subtract this overlap area from the sum of the areas of the two rectangles. This method has a constant time complexity of O(1), since it uses only basic arithmetic operations, and it also has O(1) space complexity since no additional data structures are required. However, the main limitation is that accurately determining the overlap can be tricky, especially when handling edge cases, such as when rectangles touch but do not overlap. The key insight that simplifies this process is realizing that two rectangles overlap only if their projections on both the x-axis and y-axis overlap. For the x-coordinates, this means that the maximum of the left edges of the rectangles must be less than the minimum of their right edges. Similarly, for the y-coordinates, the maximum of the bottom edges must be less than the minimum of the top edges. These conditions allow us to reliably determine whether there's an overlap and lay the foundation for calculating the overlapping area. When there is an overlap, the dimensions of the overlapping rectangle can be determined using the coordinate comparisons. Specifically, the overlap width is the difference between the smaller of the two right edges and the larger of the two left edges, while the overlap height is the difference between the smaller of the two top edges and the larger of the two bottom edges. If either of these dimensions is negative, it means there's no actual overlap, and we treat the overlap area as zero. The realization that overlap computation can be handled purely through coordinate comparisons is the breakthrough that makes the solution efficient. Building on this insight, we can streamline the brute force approach into a more optimized strategy. First, we compute the areas of the two rectangles individually. Then, we use the overlap conditions to check if the rectangles intersect. If they do, we compute the overlap area using the formulas we just discussed. Finally, we subtract this overlap area from the total area of the two rectangles. The optimized approach eliminates the need for geometric reasoning and focuses solely on simple coordinate comparisons, making it both efficient and intuitive. For example, in the code snippet, we first calculate the areas of both rectangles and then derive the overlap dimensions using the max and min functions to ensure correctness. Once we have the overlap dimensions, the next step is to compute the overlap area as the product of the overlap width and overlap height. If either dimension is 0 or negative, the overlap area will naturally be 0 due to the use of the max, 0, function. After determining the overlap area, we subtract it from the sum of the individual areas of the two rectangles to get the desired result. This approach is computationally efficient, with a time complexity of 1, since it involves a fixed number of arithmetic operations. The space complexity is also 1, as no extra memory is required. Comparing this optimized approach to the brute force method, both have the same theoretical complexity, but the optimized version is significantly less error-prone. By focusing on coordinate comparisons rather than geometric reasoning, it avoids potential pitfalls with edge cases, such as when rectangles just touch along one edge or corner. The use of max, 0, ensures that negative overlap dimensions are handled correctly, making the solution robust and reliable. Another advantage of the optimized approach is its readability. The solution is concise and easy to understand, which makes it more practical for implementation in real-world scenarios. By avoiding unnecessary complexity, it ensures that the logic remains clear and accessible. For these reasons, the optimized approach is the final choice for solving this problem. It combines efficiency, clarity, and robustness, providing a clean and effective way to calculate the combined area of two rectangles while accounting for overlaps. This method demonstrates the power of simplifying problems through key observations, such as the use of coordinate comparisons, and highlights the importance of writing solutions that are not just correct but also easy to maintain and debug. To solve the problem of finding the total area covered by two rectangles, we need to consider both their individual areas and any overlapping region to ensure we don't double count. First, let's understand the input format. Each rectangle is represented as a tuple of 4 integers. The bottom left corner is defined by the coordinates x1, y1, and the top right corner is defined by x2, y2. Using this format, we can refer to the two rectangles as rect1 equals x1, y1 and x2, y2, and rect2 equals p1, q1, p2, q2. Next, we calculate the area of each rectangle. The formula for the area of a rectangle is straightforward, x2, x1, asterisk, y2, y1. Using this, we compute area 1 for the first rectangle and area 2 for the second rectangle. These steps give us the individual areas needed for the final calculation. Now, we determine whether the two rectangles overlap and calculate the dimensions of the overlapping region if it exists. The overlapping rectangle's bottom left corner is given by the maximum of the lower bounds, overlap_x1 equals max, x1, p1, and overlap underscore y1 equals max, y1, q1. Similarly, the top right corner is given by the minimum of the upper bounds, overlap underscore x2 equals min, x2, p2, and overlap underscore y2 equals min, y2, q2. However, we need to confirm that these coordinates form a valid rectangle. This occurs only if overlap underscore x1 overlap underscore x2 and overlap underscore y1 overlap underscore y2. If this condition is met, the rectangles overlap, and the overlapping area can be calculated using the formula overlap underscore area equals overlap underscore x2 overlap underscore x1 asterisk overlap underscore y2 overlap underscore y1. If the coordinates do not satisfy these conditions, the rectangles do not overlap, and the overlapping area is 0. In cases where the rectangles do not overlap, we set overlap underscore area to 0. With the overlap area determined, we can now compute the total area covered by both rectangles. This is done using the formula total underscore area equals area 1 plus area 2 overlap underscore area. Subtracting the overlap area ensures that the shared region between the rectangles is not counted twice. There are several key insights to note here. First, the detection of overlap relies on the intersection of the horizontal and vertical projections of the rectangles, which is why we use max and min to find the coordinates of the overlapping region. Second, this approach is highly efficient, operating in constant time, O1, since it involves only a sequence of simple arithmetic operations. Finally, we need to handle edge cases carefully. For example, when the rectangles do not overlap, the algorithm should correctly identify this and ensure that no invalid overlap area is subtracted. Additionally, there are two specific edge cases to consider. When one rectangle completely encloses the other, the overlap area will equal the area of the smaller rectangle. Another edge case occurs when a rectangle has zero area, which happens if either x1 equals x2 or y1 equals y2, making it a degenerate rectangle. This algorithm does not require complex data structures. Simple tuples or arrays are sufficient to represent the rectangle coordinates. To illustrate these concepts, let's walk through an example. Suppose the input rectangles are rect1 equals 0, 0, 3, 3, and rect2 equals 1, 1, 4, 4. First, we compute the individual areas. For rect1, the area is open parenthesis 3 minus 0 close parenthesis times open parenthesis 3 minus 0 close parenthesis is equal to 9. For rect2, the area is open parenthesis 4 minus 1 close parenthesis times open parenthesis 4 minus 1 close parenthesis is equal to 9. With the individual areas calculated, we proceed to find the coordinates of the overlapping region. The coordinates of the overlapping region are computed as follows. Overlap underscore x1 equals max, 0, 1 equals 1, overlap underscore y1 equals max, 0, 1 equals 1, overlap underscore x2 equals min, 3, 4 equals 3, and overlap underscore y2 equals min, 3, 4 equals 3. Since overlap underscore x1 overlap underscore x2 and overlap underscore y1 overlap underscore y2, the rectangles do overlap. The overlap area is then calculated as open parenthesis 3 minus 1 close parenthesis times open parenthesis 3 minus 1 close parenthesis is equal to 4. Finally, we compute the total area covered by both rectangles using the formula total underscore area equals area 1 plus area 2 overlap underscore area equals 9 plus 9 minus 4 is equal to 14. The output of the algorithm is the total area covered, which in this example is 14. To optimize this approach further, we can avoid redundant calculations by checking for overlap validity early. Additionally, handling edge cases explicitly ensures the algorithm remains robust for all input scenarios. This solution computes the total area covered by two rectangles while accounting for their overlap. The compute area function begins by calculating the area of each rectangle individually using the formula width asterisk height. Rectangle A's area is determined using its coordinates, x1, I1, x2, I2, and rectangle B's area is calculated similarly from bx1, by 1, bx2, by 2. Next, the function calculates the dimensions of the overlapping region, if any. The overlap width is determined by finding the horizontal intersection range between the two rectangles, using max, 0, min, x2, bx2, max, x1, bx1. This ensures that if the rectangles do not overlap horizontally, the width is 0. Similarly, the overlap height is computed from the vertical intersection range with max, 0, min, I2 by 2, max, I1 by 1. These calculations guarantee non-negative dimensions for the overlap. The overlap area is then calculated as overlap width * overlap height. To avoid double counting the overlapping region, this area is subtracted from the sum of the individual areas of the rectangles. The final result, stored in total area, represents the combined area covered by both rectangles. This implementation handles edge cases where the rectangles do not overlap at all or overlap only partially. It ensures correctness by using max and min functions to compute the intersection boundaries. The algorithm runs in constant time, O(1), as it involves only arithmetic operations and comparisons. This is the Java implementation of the rectangle area problem, LeetCode number 223. The logic mirrors the provided Python implementation, with adjustments for Java-specific syntax and type declarations. Key differences include explicit use of math.max and math.min for calculations, and the overall class structure required for Java. The method computes the total area of two rectangles, subtracting the overlap area to avoid double counting. To solve this problem, we start by calculating the area of each rectangle individually. For rectangle A, its bottom left corner is at -3, 0, and the top right corner is at 3, 4. To find the width, we subtract the x-coordinates. 3 minus -3 gives us 6. Similarly, the height is the difference between the y-coordinates, 4 minus 0, which equals 4. Multiplying width and height, the area of rectangle A is 6 times 4, which equals 24. Now, for rectangle B, its bottom left corner is at 0, -1, and the top right corner is at 9, 2. The width is 9 minus 0, which equals 9, and the height is 2 minus -1, which equals 3. Multiplying these, the area of rectangle B is 9 times 3, or 27. Next, we calculate the dimensions of the overlapping region. The width of the overlap is determined by finding the maximum of 0 and the difference between the smallest top right x-coordinate and the largest bottom left x-coordinate. This calculation gives us an overlap width of 3. Similarly, the height of the overlap is the maximum of 0 and the difference between the smallest top right y-coordinate and the largest bottom left y-coordinate, which results in an overlap height of 2. The overlap area is then 3 times 2, which equals 6. Finally, the total combined area is the sum of the two rectangle areas minus the overlap area. Adding 24 and 27 gives 51, and subtracting the overlap area of 6, we get a total area of 45. In this example, the output is 45, which matches our calculated total area. Now let's consider a different scenario where the rectangles do not overlap. Rectangle A remains the same, so its area is still 24. For rectangle B, its bottom left corner is at 4, -1, and its top right corner is at 6, 2. The width is 6 minus 4, which equals 2, and the height is 2 minus -1, which equals 3. Multiplying these, the area of rectangle B is 2 times 3, or 6. Next, we check for overlap. The overlap width is determined by the maximum of 0 and the difference between the smallest top right x-coordinate and the largest bottom left x-coordinate. Here, the calculation results in -1, so the overlap width is 0. Similarly, the overlap height is determined as before, but since the width is 0, there is no overlapping region, and the overlap area is 0. The total combined area is therefore the sum of the two rectangle areas, which is 24 plus 6, resulting in 30. The output for this example is 30, which reflects the combined area of the two non-overlapping rectangles. Now consider a case where one rectangle completely overlaps the other. Rectangle A spans from 0, 0 to 2, 2, and we calculate its area as before. The width is 2 minus 0, which equals 2, and the height is also 2 minus 0, which equals 2. Multiplying these, the area is 2 times 2, or 4. Rectangle B has the same dimensions and coordinates as rectangle A, so its area is also 4. To calculate the overlapping region, we determine the overlap width and height. Since rectangle B fully overlaps rectangle A, the width and height of the overlap are the same as the dimensions of either rectangle, 2 for both width and height. The overlap area is therefore 2 times 2, which equals 4. Finally, the total combined area is calculated as the sum of the two rectangle areas minus the overlap area. Adding 4 and 4 gives 8, and subtracting the overlap area of 4, we get a total area of 4. The output for this case is 4, which makes sense since one rectangle is entirely contained within the other, so the total area is simply the area of one rectangle. These examples demonstrate how the solution handles partial overlaps, no overlaps, and full overlaps, ensuring that all cases are covered. To analyze the time complexity of the compute area function, we first look at how each component is calculated. For rectangle A, the area is determined using the formula x2 x1 asterisk I2 I1. This involves two subtractions and a multiplication, each of which is a constant time operation, or O1. Similarly, the area of rectangle B is computed using the same type of formula, bx2 bx1 asterisk by 2 by 1, which also takes constant time. Next, we calculate the overlap area, which involves determining the overlap width and height. For the width, the calculation max 0 min x2 bx2 max x1 bx1 includes two min operations, two max operations, and a subtraction, all of which are O1. A height calculation follows the same logic. Once we have the overlap width and height, multiplying them to get the overlap area is again an O1 operation. Finally, the total area is obtained by adding the areas of the two rectangles and subtracting the overlap area. This involves two additions and one subtraction, all of which are constant time. Therefore, each step in the computation is O1. When we sum up all these constant time operations, the overall time complexity of the function is O1. This means that no matter the size or position of the rectangles, the number of operations remains fixed and does not grow with the input. Now, looking at the space complexity, we analyze the memory usage. The function takes 8 integers as input, each requiring O1 space. Additionally, it uses a few intermediate variables: area A, area B, overlap width, overlap height, overlap area, and total area. Each of these is a single integer, so they also require O1 space collectively. Since no additional data structures or dynamic memory allocation are used, the space complexity of this function is also O1, independent of the input size. To understand the efficiency of this optimized approach, consider a brute force or naive solution. One such method might involve iterating over every point within the bounding box of the two rectangles to check for overlapping points. For example, you could loop through all x coordinates from min x1 bx1 to max x2 bx2, and all y coordinates from min I1 by 1 to max I2 by 2. This would be proportional to the area of the bounding box, leading to a time complexity of O(n) squared for large rectangles, which is highly inefficient. In contrast, the current solution avoids such inefficiency by directly calculating the overlap dimensions using algebraic operations like min and max. These operations reduce the time complexity to O1, making it significantly more efficient. Additionally, because the algorithm uses a fixed number of operations, the best, average, and worst-case scenarios all result in the same time complexity, O1. To solidify our understanding, let's examine why the big O of this optimized solution is O1. First, the number of operations performed is constant arithmetic, min, and max calculations are performed in a fixed sequence, regardless of the size or values of the inputs. This means the time taken does not scale with the input size. Similarly, the memory usage is fixed because only a constant number of variables are used to store intermediate results. Since neither the time complexity nor the space complexity grows with the input, the algorithm is optimal for this problem. There are no further improvements possible in terms of efficiency, making this a highly optimized solution. One of the most common mistakes when solving the rectangle area problem is incorrectly calculating the overlap region. This usually happens when we forget to first check if the rectangles overlap at all. For instance, if two rectangles are completely disjoint, attempting to calculate an overlap can lead to invalid results. To avoid this, it's critical to use proper boundary checks like confirming that the right side of one rectangle is greater than the left side of the other, and that the top side of one rectangle is higher than the bottom of the other. Another frequent issue arises when handling negative coordinates. Since the Cartesian plane includes both positive and negative values, it's easy to get confused when determining boundaries. A reliable way to handle this is by consistently using functions like max and min to compute the limits of the overlap. This ensures you're always selecting the correct boundaries regardless of the coordinate signs. Additionally, many overcomplicate their logic for overlap detection. Overly nested conditionals or redundant checks can make the code harder to debug. Instead, focus on directly computing the overlap boundaries with straightforward formulas. Finally, edge cases like rectangles being fully contained within one another or just barely touching along an edge or a corner are often overlooked. Testing your code with such cases can help you catch these scenarios early and ensure robust solutions. Another mistake to watch for is sticking to a brute force approach without considering optimizations. While brute force might work for simpler examples, it's not ideal for time-sensitive interviews where efficiency matters. Instead, think about the trade-offs and explore geometry-based optimizations that improve clarity and performance. A key insight to keep in mind is that the overlap between two rectangles is entirely determined by their boundaries. Using functions like max and min simplifies the process of computing the overlap region efficiently. During an interview, it's also important to clarify the problem constraints with your interviewer. For example, can rectangles have zero area? Are all inputs guaranteed to be valid? These questions help eliminate ambiguity and show that you're thorough. Writing clean, modular code is another important practice. By creating reusable functions to calculate areas and overlaps, you make your solution easier to debug and adapt if the requirements change. Lastly, if the problem involves scaling to multiple rectangles, make sure to discuss advanced strategies like sweepline algorithms or segment trees. Even if you don't implement them fully, showing an understanding of their use cases demonstrates your ability to handle more complex scenarios. This problem also connects to several related challenges on LeetCode, such as Problem 836, which focuses specifically on determining whether two rectangles overlap, and Problem 850, which extends the concept to calculating the union area of multiple rectangles. Another interesting variation is Problem 391, which deals with checking if a set of rectangles can form a perfect rectangle without gaps or overlaps. Exploring these problems can deepen your understanding of geometry-based questions. When it comes to alternative approaches, the brute force method is the most straightforward. It involves directly calculating areas and overlaps, which is easy to implement but becomes inefficient as the number of rectangles increases. For scenarios involving multiple rectangles, the sweepline algorithm is a powerful tool. By sorting events and managing active intervals, it enables efficient calculation of the union area. However, this approach comes with the trade-off of added implementation complexity. For even more dynamic scenarios, the segment tree is a useful data structure for managing overlapping intervals in two-dimensional space. While it offers efficient updates and queries, it's also space-intensive and requires a solid understanding of the underlying principles. Choosing the best approach depends on the problem's constraints and the level of optimization required. Great job making it to the end. In this session, we tackled the rectangle area problem, breaking it down into manageable steps. We highlighted the brute force approach, discussed its complexity, and extracted key insights. Remember, understanding overlaps and geometric reasoning is vital in many applications. Thanks for watching, and be sure to check out more coding problems and solutions on our channel. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!